So hello everyone and welcome to my talk. My name is Ralph Palutke and I'm here for the Friedrich Alexander University of Erlangen-Nuremberg, where I am part of the IT security research team. As for today's talk, I want to present HyperLeech and elaborate the topic of stealthy system virtualization with minimal target impact through DMA-based hypervisor injection. So to start out my talk and motivate the topic, malware has shown an increased incorporation of anti-forensics in order to evade analysis. So therefore, we have an increased need for stealthy analysis techniques that are robust against these anti-forensics. And over the past, there emerged two approaches that seem to be the most promising, which is on the one hand, approaches that rely on direct memory access, as DMA offers the transparent analysis of a target system from mostly external hardware with almost no target impact. And as many of these devices are hot pluggable, they can even be deployed during the runtime of the analyzed system. However, DMA-based approaches lack in atomicity due to the system's concurrent execution, as the CPUs are not interfered, as well as a miss of context information due to the well-known semantic gap. On the other hand, we have virtualization-based approaches, which basically shift the analysis method into a more isolated and privileged hypervisor layer. However, these approaches suffer from different kinds of issues, mostly modifications of the target state, as well as the need for elevated permissions on the target system and allow malwares to subvert the installation process in the first place. So in order to allow the analysis to be correct and sound, we define a few terms, which is on the one hand, the soundness of a method, which can be defined as its robustness against anti-forensics. So in other words, the possibility to produce correct results in potentially compromised environments, as well as its target impact, which is defined as the amount of modifications introduced by a particular analysis method. And of course, the lower the target impact, the better, as it prevents a loss of evidence, as well as malware to alter its behavior. So the ultimate goal of our research was to leverage virtualization, as it provides a more privileged execution layer, however, without affecting the target states during its installation, operation, and removal. So before I'm gonna present our actual system, I wanna give a brief introduction over Intel's virtual machine extensions, which builds the basis or foundation of our work. So Intel's virtual machine extensions basically allow unmodified guests to run inside hardware accelerated virtual machines by expanding the instruction set of modern Intel processors. VMX adds an orthogonal execution mode, which is called VMX operation, that can be further subdivided into VMX root mode, which serves the hypervisor as an unrestricted and privileged execution mode, as well as VMX non-root mode, which serves the guest system as a restricted execution environment. To switch between those two modes, Intel introduces so-called VMX transitions, which basically occur whenever a guest encounters certain events and therefore triggers a VM exit, which subsequently transfers control to the hypervisor. The hypervisor then has the chance to handle the event and resume the guest by generating a VM entry. The actual configuration of a virtual machine is done through a virtual machine control structure, which is basically used to store the state of the guest whenever we are in VMX root mode, and can be configured for the hypervisor to intercept certain events and so on. Next to these virtual machine extensions, Intel introduced the so-called extended page tables, which is a second level address translation in order to help the hypervisor to virtual the physical memory of the guest system. And like with the usual page tables of an operating system, extended page tables provide access permissions in order to control the accesses to certain memory areas. And if these permissions are breached, now similar to a page fault, an EPT violation occurs, which can be intercepted by the hypervisor, and the hypervisor then has the chance for example, to restrict the guest from accessing certain memory areas. So with that being said, we now have the foundation to understand the design decisions we made for our HyperLeech system. So our main contribution was to combine DMA-based code injection with runtime virtualization in order to establish a stealthy injection and removal process for a hypervisor through DMA and shift a running target system into a hardware-accelerated virtual machine. We provided proof of concept implementation that currently targets multi-core Linux hosts and evaluated its target impact. Which as a result seemed to be very, very low, and therefore it is applicable for stealthy system analysis. Lastly, we discussed some mitigation strategies in order to prevent our system to be misused as a very powerful and advanced rootkit. So we first want to give an architectural overview of our system, which basically comprises two components, which is on the one hand a target host as well as an analysis host on the other hand. And in order to access the target memory via DMA, we used HyperLeech, which is a generic attack framework for code injection developed by Ulf Frisk. And it does not even require any privileges or drivers to be installed on the target system. While HyperLeech runs on a wide variety of hardware configurations, we decided to use a special FPGA hardware, which is called the PCIe Screamer, as it provides native 64-bit DMA with access rates around 100 megabits per second, and it connects over USB 3 to our dedicated analysis host. As it provides hot plugging capabilities, it can even be deployed during runtime, which is of course a nice thing for forensic purposes. On the analysis host, we have an agent running, which serves an analyst as a control interface, and it communicates with the PCIe Screamer hardware over a dedicated HyperLeech host software. So in the next few slides, I want to give a general overview of the mode of operation of our system. And as a first step, we instruct the PCIe Screamer device to inject a small installer stub into the running Linux host kernel in order to hijack the guest kernel's execution flow, set up some additional kernel memory to place the hypervisor binary, and launch the hypervisor subsequently. Once the hypervisor is in control, it starts to transparently migrate the target system into a virtual machine, similar to a hypervisor rootkit, which does not even require a reboot of the target system, and the target system is not even aware of being virtualized. Yeah, since we are sharing the memory with the target, we somehow have to isolate the hypervisor's memory, and therefore we use the extended page table mechanism I've mentioned in the previous slides. So once fully installed and the guest is running in a virtual machine, our system serves as a stealthy and privileged execution layer in order to allow stealthy system analysis on the hypervisor layer. So as we are more privileged even than the guest kernel, we can now analyze kernel malware, create memory dumps, or deploy log forensics through virtual machine introspections. This is all approaches that have been shown in the past and that can be included into our systems. For the actual control of the hypervisor, as well as the extraction of information from the target host, we use the already established DMA channel, as it is very transparent to the guest. So therefore, we do not have to extract information over network cards or and somehow modify the state of the guest. So with that being said, I want to give a few more technical details on the actual injection of the hypervisor. And we decided to show the injection here. Similar things can be said about the removal. However, due to timing constraints, we're going to focus on the injection here. So the process of injecting a hypervisor is split into multiple so-called injection stages, which we optimized to minimize target kernel dependencies, as well as preserving target and memory processor state as best as they can, which is of course a nice thing from a forensic point of view. So we're going to start out by localizing the kernel space image, which is actually randomized by modern systems due to usage of KASLR. And therefore, we issue DMA to scan the entire physical memory and compare each page that we read to a pre-registered signature of a first kernel page, which of course is version dependent. However, we found out this works very successful, and it's very fast, so we can easily determine the kernel space address. So before we're gonna inject any code into the running kernel, we make sure to store the original content of certain areas to the analysis host. And we then did some research to find good injection spots, and we found that the kernel's first code page offers some space for our injected code, as it comprises mostly NOP instructions, which do not have any functional purpose and can therefore safely be overwritten without risking any severe system failures. In addition, we somehow had to hook the kernel's control flow in order to withdraw control from it and hijack its control flow so that we can execute our own code. And we determined the kernel's idle routine to be a good candidate, as it is regularly executed by each processor and provides ring zero privileges, which are required for the actual setup of the hypervisor. So once installed, as soon as a processor enters its idle state, it will also enter our hook, and therefore we can withdraw control from this processor, which is done for all processors installed in the system. So we now have full control over the entire system. Once we enter the next stage, we now have to ensure that processor execution is somehow serialized in order to prevent concurrency issues. So therefore, we invite global lock, which is basically forcing processes that are already virtualized back into the idle loop without entering the subsequent stages. Because these stages also alter the process state to a slight extent, we use the kernel stacks to preserve its state, as we do not have a lot of space at this early stage of the injections process. The next stage is basically responsible for setting up the actual hypervisor, and it starts out by disabling interrupts to prevent the target from disrupting the injection process. And as a small side note, disabling non-maskable interrupts needed the local epics to be reprogrammed. In addition, we request some memory for from the target kernel via the kmalloc interface in order to place our hypervisor binary later on. And we found out that a single 2 MB page seemed to be sufficient for this hypervisor area. After storing the content of the hypervisor area, the original content from the hypervisor area back to the analysis machine, we can now copy the hypervisor binary to this area and switch to its memory layout so that it can execute its own code. And once the hypervisor is in control, it starts out by registering a custom non-maskable interrupt handler, which is required before enabling NMIs, as any missing NMI could potentially corrupt our target system. And the handler is basically responsible for re-injecting any of these pending NMIs whenever it re-enters the guest. For state preservations, we now have enough space for setting up our own stacks, and therefore do not have to pollute the kernel stacks anymore. In the last stage, the processor is actually virtualized. So we're going to enter VMX operation, prepare a virtual machine control structure in order to mimic the current target state, which is similar to our hypervisor rootkit like Blue Pill, setting up extended page tables to isolate the hypervisor area from the guest and restore the original target memory, so that we now have the original state of the kernel's code segment. We can now finally launch the virtual machine and resume the target as a virtualized guest by returning it into the original execution inside the idle loop where we first withdraw control from it. And then HyperLeech is fully installed and ready to perform any kinds of stealthy analysis tasks. I now want to give a few more details on the actual operation of our system, especially regarding the isolation of its memory. So like I've said before, the hypervisor area is fully isolated from the guest by configuring extended page tables so that they trigger an EPT violation whenever a page within the hypervisor area is accessed by the guest. And we simply redirect all of these accesses to a specifically prepared guard page, which on the graphics on the right is depicted as the host physical page H2. The remaining guest memory is identity mapped, meaning that the hypervisor does not have to interfere. And we invented an update mechanism in order to preserve modifications of the hypervisor area, which I will now explain in the next few slides. So we only have one present mapping to the guard page at a time. So in the graphics on the right, we can see that the guest physical page G1 is currently mapped to the guard page. So when the guest wants to override G1, it now is redirected to guard page and reflected on the host physical page of H2. So therefore, no hypervisor intervention is necessary. A more interesting situation arises whenever the guest wants to access a page that is not currently mapped in the extended page tables, as now an EPT violation occurs and control is given back to the hypervisor, which now has the chance to instruct the agent to swap memory contents. So in case the guest wants to access the guest physical page G3, we will trigger an EPT violation, and the hypervisor can swap out the contents of G1 back to the analysis machine and swap in the intended content of G3 before reconfiguring the EPTs and allow the guests to access the intended memory. And therefore, the hypervisor area stays always up to date. So we then evaluated our system regarding its target impact during the phases of injection, operation, and removal. We used Debian Stretch as our target operating system with an Intel Cindy Bridge CPU for the target host, 4 GB RAM, and a Fujitsu motherboard. And on the analysis host, we used Windows 10 Enterprise and had to install the FTDI USB drivers in order to communicate with the PCI Leech firmware. Like I've mentioned before, we used PCIe Screamer in order to gain a DMA on the target machine, which had to be flashed with the PCI Leech firmware. So during the injection removal, we found out that, of course, the injected stages had to replace some of the target's memory, but this is not a big problem as the agent had initially preserved the content back to the analysis machine. Further on, the actual execution of the injected code alters the target state to a slight extent, but we have optimized our stages to preserve the memory and processor state. Allocating the hypervisor area also modifies a few certain kernel data structures, like a few page table entries, as well as a few entries in the slat allocators. However, as the injection removal only lasts for a few seconds, most of these modifications are not generically detectable in our mind. So the more interesting thing is once the system has been fully installed, as the agent now has restored the kernel's code segment, which leaves us only with a few slightly altered kernel stacks, which these modifications occurred due to the state preservations during I2, which we consider to be practically undetectable as the kernel constantly overwrites stacks once it is resumed anyway. And then we have the few kernel structures I've mentioned in the last slide that reference the hypervisor area. However, as all of these accesses are redirected to our guard page with the mechanism as shown in the last chapter, no traces can be found by following these references. And of course, usually the kernel won't ever legitimately access a k-malloced area anyway. So after cleaning up our system, no relevant process state is ever lost, with the exception of the few negligible modifications of the kernel stacks. However, attaching the PCIe screamer device introduces some detectable modifications, as the kernel enumerates the PCIe bus whenever it registers a new device, and this enumeration alters the file system, memory, and processor state to a slight extent. However, the device only appears as a benign network adapter, which could further be changed by changing its device ID, so we do not think that this is a conceptual issue. So as our system could be misused as a powerful rootkit, we're going to talk about some mitigation strategies in the next few slides. The best would be, of course, to prevent the attack. And this could be done by disabling the virtual machine instruction in the BIOS or AFI. However, this, of course, would deprive the legitimate usage of virtualization, which is probably not a good idea nowadays. We could also prohibit the attachment of additional PCIe devices, but it would restrict the user from adding additional hardware. So we think the best solution would be to restrict DMA to certain areas by configuring an IO MMU. However, we found out that most operating systems don't do it per default nowadays, and recent research even showed that there are ways to bypass a fully configured IO MMU. If prevention is not possible, we could maybe detect our system. However, as the installation and removal requires only a few seconds and no significant target state has been altered once HyperLeech is installed, we are practically limited to finding indications of the actual virtualization. And researchers proposed to use side channels for timing that occur due to the hypervisor's overhead for the detection. However, as VTX allows to forge internal gas clocks, this is not as easy and straightforward as it might seem. And as virtualization becomes even more prevalent, we do not think that detecting virtualization is the correct way to detect our system in a generic way. So to conclude our talk, we presented a novel approach to inject the hypervisor through DMA using a PCI leech device, combining the advantages of DMA and virtualization in order to establish a stealthy and privileged execution layer for system analysis. We provide a proof of concept implementation, which currently targets more than multi-core Linux hosts with only a negligible impact on the state of the target system, and therefore conclude that we advance modern system analysis and memory forensics with a robust with a system that is robust against generic anti-forensics and malware subversions. With that being said, I come to the end of my talk. I thank you for your attention, and I'm very happy to answer your questions.